So, talking specifically about the topics, right? To get a detailed look into the Cassandra architecture actually. So there are some components which work at the back end, right? So they club together, um, get the things done for us, right? And might be these terms are a bit new, right? So the first half actually, right, we are going to discuss about these components. What are they? Because when actually we are going to discuss about the details, right? The actual reads, writes, or the replication distribution and whatever which happens at the back end, right? We'll be using these terms a lot in detail, right? So the terms like a snitch, the terms something like a gossip, and then something like a virtual node, and when we are about to write the data, what is a hashing, right? Replication strategy, that I'm going to create this table, this replication strategy I'm going to use. So what is the meaning of this replication strategy actually, right? So we'll be discussing all these terms, right? And we'll be discussing these terms, getting the knowledge about them, right? And we'll be using these terms in understanding the architecture in detail. Plus, whatever the terms or the components that we need to understand during the architecture discussion, we will be taking them up in the orderly fashion during our topics. All right. Okay. So the first in the line is a snitch, right? So this term actually, which is called a snitch, this is the way by which you can say that the node in a cluster know about the topology, right? Uh, it checks for the proximity of the nodes. I'm just taking the simple example, right? So for example, say that you are living in a building, right? And you live on the second floor, right? Someone else is living on the first floor, right? And he's like the next door neighbor to you, and someone who's living on the third floor is also the next door neighbor to you, right? Now this guy who's living on third floor has another next door neighbor which is living on the fourth floor, and the first next door neighbor was you, who was living on the second floor, right? So for example, say that you and the guy on the third floor talk to each other, all right? And then you then talk to the guy on the first floor regarding your interaction with the guy on the third floor, and the guy on the third floor talk to the guy on the fourth floor regarding interaction with you, right? This way, with like your interaction with the guy on the third floor and their actual interaction with other guys regarding your interaction, the guys who are there on a, like first, second, third floor, now they know about each other kind of thing. They know that, okay, I am living on first floor. My next door neighbor who's living on second floor actually talked about the guy who's living on the third floor, right? Now the guy on the first floor knows that this guy, Mr. Y, who's living on third floor, is like two floor up from me, right? Just taking this basic example. So that is a snitch. The way of communication that the nodes take up to talk to each other, right? To know about the topology, right? So we'll be discussing this snitch thing in detail, right? So let's, get ahead and discuss about the types of snitches that we have, right? So we have a simple snitch, right? A dynamic snitch, a rack inferring snitch, a property file snitch, and a gossip property file snitch. These are the 5 basic types of snitches that we have, right? Apart from that, they're like you can say that specific type of snitches, but they are not like the generalized things which are there. For example, one of them is for the Amazon EC2 services and other things, but they're like very specific to the EC2 architecture. So we'll be covering these 5, which will be there omnipresent in whatever implementation we have, right? So if we move forward, take the first one, which is the simple snitch, right? So you remember the terms from our first session, right? We discussed something about a data center and a cluster and a node. So node was a single component, a machine, right? A collection of multiple nodes or multiple machines was called a data center, referred to being like DC in this and the upcoming slides, right? And multiple data centers, which may be across different locations, were clubbed together and they formed the cluster, right? So simple snitch is generally used for clusters which have a single data center. So say that you are working with XYZ organization, and your organization has implemented Cassandra, right? And you have like 100 different nodes or machines which are you know connected to each other via a network actually, right? And all of them are present in California or whatever location that you are putting up or your office is, right? That's a single data center. And you do not have any other Cassandra machine across any other location or in any other data center. That's a cluster which is of a single data center, right? So simple snitch is used for a single data center cluster, right? Now the simple snitch is rack aware, because in this particular case I'm going to have a single data center, all the machines present at one particular place, nothing like that, right? The strategy in this particular case is that, for example, when I'm about to write the data, right, we learn about the replication thing as well, right? And the replication, we discussed that, for example, if I'm writing to machine 1, it will write, or you can say that, replicate the data to two other machines which are next in the clockwise, right? In this case, this is the strategy to place the data and how the machines communicate, right? So if I can take you to one particular slide, just take this example, right? Can you see this one? In this particular case, I have a node A, right? A node B, C, D, E, and F. This node A will talk to node B and node F, all right? The next door neighbors. This B will talk to C, this F will talk to E, and so on. And this is called a simple snitch kind of thing, in which a node talks to its next door neighbors to pass the information that it has regarding any other node, right? So for example, A talks to F and A talks to B, right? Now node F and node B has some information regarding A, and that information is regarding the presence, the IP address or the host name, or whatever data is present, or whatever range of data is present with A. The machine F in turn will share its details with E, and also the details about machine A that it has. So that's like a gossip, right? And we have heard this thing a lot regarding women's, right? So women talk something to one of her friends, tell her not to share it with anyone else, but that friend end up sharing everything with everyone, right? Gossip, of course, this is something which is happening here in my Cassandra cluster as well, right? So that is the basic type of the snitch that I have, the simple snitch, right? The nodes talk to the next door neighbors or the neighboring nodes regarding whatever information they have regarding itself, and of course about some other nodes, because if this information is not regarding some other nodes, that will not qualify as a gossip, right? The other type of snitch that I have is a property file snitch. In a property file snitch, right, it overcomes the limitation of the simple snitch. A simple snitch actually can only talk to the machines or the nodes which are there, just neighboring each other, right? That is a single data center. If I have more than one data center, a simple snitch will not be actually, which might make the communication across the machine happen, right? In that case, I need to use something else. A property file snitch comes for my rescue actually in that particular case, right? Uh, a property file snatch is rack aware, that it knows that, okay, I have separate racks, one present here, one present at some other place, with n number of nodes in every rack, right? And it determines the proximity, that how far the rack or the node is, based upon the information of the rack and the data center, right? So there is this file which is called Cassandra-topology.properties file. It has some information regarding the data center and the rack, which makes it possible to deduce that where this particular node is present. So in this particular slide, if you can see this, right, and please take care of this note, that the data center and the rack names are case sensitive, right? So what I have mentioned is, say, take an example, I have two data centers. Just take that example, right? Data center 1 and data center 2. Data center 1 present at some other location, say United States of America, and data center 2 present in somewhere in France, right? Uh, these data centers, as we know that data center is a collection of multiple nodes, right? These data centers may have multiple nodes present inside that, and those nodes may be clubbed inside smaller racks, right? I hope you understand this term rack actually, right? It's a collection of multiple machines stacked up, right? And in this particular, if you see, right, in data center 1, I have a particular IP address and it is equal to this, and then this is the structure of my this file, Cassandra topology.properties file. How does it looks like? Something like this. An IP address of whatever machine equal to then to which particular data center and which particular rack it belongs to. So from data center 1, it belongs to rack 1. Similarly, there is another machine which is in data center 1 and belongs to rack 1. The third machine here starts with 120.53.24.101, right? It actually is in data center 1 but belongs to rack 2. The second machine is in data center 1 but belongs to rack 2. So I have two racks in the first data center having two machines each. Then there is another data center which might be at some other different locations or something. You know, it has the data center labeled as DC2, and both the machines listed here are in the data center 2 but from the same rack, right? So when identifying actually, right, every node every node in my data center or in my rack will have this file updated, Cassandra topology.properties file, having the information about every node, that where this node is present in the same rack or in the same data center, right? Or might be in a different data center. So this value, right, helps identifying a particular node, that the node it is going to talk about or discuss to or get the data from, that will look actually in detail later on, right, that where it is present, right? If the data center values match, it's in the same data center. And if after the matching the data center values, if the rack values also match, rack 1, it's in the same rack, right? If not, different rack or different server altogether. The issue here is actually, right, if I am gonna maintain all these details in a particular properties file, right, what may happen is, say I have, for example, 100 nodes as of now, 50 in the first data center, 50 in the second data center. My plan is actually to double the capacity, right? If I have the plan to double the capacity and install 50 data nodes, 50 nodes in the first data center and 50 nodes in the second data center, the thing is, I actually need to update this Cassandra topology.properties file for all the new addition of 100 nodes. Plus, I also need to maintain or update this file for the existing 100 nodes with the address of the new nodes, which actually will be a part of this same cluster. Doesn't matter in the same data center or the different data center, but at the end of the day, they'll be ending up forming a cluster, right? And because these 100 nodes are already present, and the other 100 nodes which will be added will be, they'll belong to the same data center, I need to make sure that I have ample information about every single node which is there in my cluster. How to do that? Update the Cassandra topology.properties file. Doesn't gonna work actually, right? Because it will need a lot of manual effort, right? Overcome that, again have this thing, gossiping property file snatch, right? A gossiping property file snatch is nothing but just an extension of property file snatch, right? This is highly recommended for production, right? In this particular case, we do not need to update the topology file in case of any addition of a node or any deletion of a node. Take this thing again. For example, if I have 100 nodes and I want to take down 10 nodes from that particular cluster, I need to update the topology file for rest of the 90, telling them that this particular 10 nodes are no more present in my cluster. Do not try to interact with them. I need to make an update to the Cassandra topology.property file, right? In gossiping property file snatch, I need to do that. Why? What it does is, it actually uses the rack and the data center information which is present in every data node, or every node actually, by the way. So this file, this Cassandra dot rackdc dot properties file, right, it has the information, right? And we discuss about the gossiping thing, right? So one node talks to another node regarding, of course, its own properties and the properties of whatever machine it knows about, right? And propagate the changes via gossip. right? The Cassandra -ragdc.properties file actually what it defines, if you see at the bottom, it defines that DC property should be equal to the name of the data center, and the rack property should be equal to the name of the rack, right? So again, a note: data center and the rack names are again case sensitive, right? So if I take this example and if I skip a bunch of slides here, right, I have this structure where I have like 6 nodes present in my cluster or my data center: A, B, C, D, E, and F. Now this node A will have this file, which is the Cassandra-rackdc.properties, with something which looks like the value of the data center and the value of the rack, right? When a gossip will happen, this A will tell B and F regarding the properties of or you can say the values of its rack and the data center component, right? Now this machine F knows about its own data center and the rack, and of course about the data center and the rack value of node A. When this machine F will talk to this machine E, it will propagate the details about itself, node F, and also node A. And this propagation will keep on happening across the cluster, across the data centers, until and unless I have all the details regarding all the nodes. So in this case, even if I'm actually deleting any particular node, right, I don't need to go ahead and update that Cassandra-properties file actually, right? Cassandra-topology.properties file. Why? Because I'm not hard coding the information about rest of the n-1 nodes into the Cassandra-topology.properties file. How the information will propagate, that will happen via the gossip, which happens almost every second, right? The information is exchanged across the nodes, right? This is kind of a dynamic thing which is there. I don't need to actually maintain a topology file, right? Hence removing the effort to manually update that. All right, so I hope that we are clear here with the difference between a property file snitch and a gossiping property file snitch. A gossiping property file snatch is still using the data center and the rack values. The difference here is I don't need to hard code it. The values will be propagated via this gossip. Alright. The next one is the rack inference. The rack inference snatch is very much similar to our gossiping property file snatch, right? Or the property file snatch, say, right? But in this particular case, we are not going to maintain any particular properties file. Topology properties file, right? Well, we're not going to say something like DC or the data center equal to this particular name and rack is equal to this particular name or whatever, right? We know that every machine which is there in the network is supposed to have an IP address. We know how the IP address looks like, right? We have like 4 different octets, or we can say that 4 different fragments to a particular IP address, right? Separated by a dot, right? So how does that looks like, right? Take the example of this particular sample IP address. The IP address looks like 110.100.200.105. The second octet, actually, this represent the data center octet, right? Using this second octet, I can identify that whatever IP address which has 100 as the second octet belongs to the same data center, right? The third octet that I have, right? If any IP address having the third octet as 200, right? We call it as the rack octet, means it belongs to the same data center. The last one, of course, 105 is something which actually uniquely identifies a particular machine, right? So while actually maintaining the network, while actually doing the networking, we need to take care of that the machines which are actually belonging to the same rack should have the same third octet, and the machines which are belonging to the same data center should have the same second octet, right? In this way, you know, my nodes, right, will read the IP address, right, will uh, figure out that which particular data center it belongs to and which particular rack it belongs to, and the last octet, of course, is something which is unique to every machine. right? We have discussed about this gossip thing here, gossiping property files, that you know the machine will talk to each other, the neighboring nodes, and get the information fast, right? Talking about the gossip, or we can say that an internode communication, right, in detail, right? So this gossip is a peer-to-peer communication protocol. Every node or every machine exchanges the information regarding its state, right, to the neighboring nodes. And not only about itself, it will also exchange the information about whatever nodes they know about, right? Essentially, actually terming it as a gossip, right? This process runs actually every second and exchange, of course, the state messages, right? With all the neighboring nodes which are there, right? Will it, of course, it'll exchange the information regarding itself and the other nodes that they gossip about. So this way, the benefit is, right, not every machine needs to talk to every other machine, right? The propagation will be something like, you can say that, proportional, right? So one machine talks to the two other machines talk to two other next other machines, right, and so on, right? All the machines learn about every machine that way very quickly, right? And all the whatever you can say that information, the state information or the metadata information is actually passed to every machine inside the cluster, right? So a gossip message, whenever propagated, has a version associated to that, right? So that whenever a newer version of the gossip is propagated, right, it should override the older information which is already present with the node, right? So if you can actually just think about the gossip property file snitch that we discussed about, in which the data center information and the rack information is sent across to the other machines, right? Removing the dependency on Cassandra hyphen topology dot properties file, right? So if I have, say, I have 100 nodes, and every node will have the information regarding 99 separate nodes, right? So if I do not get the information about 10 nodes, right, after a particular point of time, they'll be erased, right? Essentially, telling my node that I only have, right, like 89 nodes now in the cluster, right? Because I have the information regarding those 89 nodes, right? And hence making it dynamic, right? The next thing which we are going to discuss is something called a virtual node, right? We have discussed the things, something like that, hey, actually I'm going to have like these number of nodes in my data center, or this much number of nodes in my data center, right? That makes sense, right? So for example, if I have like 10 different machines clubbed together to form a Cassandra cluster, I'll say that yes, I have 10 different nodes present with me, right? They are physical nodes, right? For a certain reason, to make the availability better and the downtime even less, right? What we did, and that's something which started with Cassandra 2, right? Or 1.2, sorry, if I'm not wrong, right? Prior to that, we hadn't had this concept of virtual nodes, right? What is a virtual node? Actually, a particular node is divided into, or you can say that a physical node is divided into very smaller fragments, right, of a particular ranges. We'll discuss about that thing in detail, the ranges thing or the token range thing, which is there, right, when we are going to discuss about the reads and the write operations, right? So this drawing an analogy, right? For example, if I buy a laptop and this laptop has 500 GB of disk space available, right, I can either use that disk as a single partition, right? Okay. I can either use that hard disk as a single partition, having all the 500 gigs available there, or what I can do is I can actually break that hard disk into smaller fragments we call as partitions. So the first partition is of 100 gigs, which is the C drive, and it is going to hold all my installation related information, the files which are there, the Windows 7 and other installation properties there. The next partition is of 100 gigs again. It's actually gonna hold all my music. The next partition is like 100 gigs again. It's gonna hold my movies, and so on. I can have two separate other partitions having separate kind of data within there. A virtual node is similar to a partition of a hard disk. A hard disk is a physical entity. A partition is a logical one, right? So if I have a machine a present machine, right, I'm going to divide it into smaller logical fragments or partitions. We term it as a V node, right? Uh, it helps in actually a better distribution of data. How actually we'll discuss that in detail, right? By default, there are like 256 partitions which are created per node, right? But that can be adjusted, by the way, right? No issues at all with that, right? We can take care of that particular part. For example, no, where it is actually important. For example, say that I have created a cluster with 100 nodes, right? Every node has this configuration of something like, say I'm just taking an example, say that 32 GB of RAM and a certain processor, right, and a certain amount of hard disk which is available. Now after 3 years, right, I feel that need of having more machines added to my cluster. But with the evolution of technology, I can now easily afford 64 GB machines, which are actually double the fast as compared to my 32 GB machines. It has a better processor as well, right? In that case, I know that my 32 GB machines were having like 256 partitions, right? Now my newer machines, which are double the powerful, what I can do is I can actually make more than 256 partitions there, just to make sure that you know I have more data to be served by the stronger machines, so that I do not have like lagging machines in my machines which are actually making the lookup time less in lookup time more, and then the lookup speed less, or the scan speed less in my cluster, right? So I can actually assign more partitions to my powerful machines, right, and less number of partitions to my less powerful machines, right? We'll see that how actually it helps there. And use consistent hashing to distribute the data. Again, we'll have a look into that while we are gonna create or we are gonna actually discuss about the write operations which happen at the back, right? Taking an example, this slide, I was coming up to it again and again to have a discussion about the gossip thing that we were talking about, or the snitches thing I was talking about. This actually is an actual cluster, right? Having 6 nodes: A, B, C, D, E, and F, right? Taking an example, right? So say that this is node 1, right? It's like some kind of a misleading thing which is there. So I have like 6 nodes present, right? So you can call this A, B, C, D, E, F as 1, 2, 3, 4, 5, 6, right? I have 6 nodes, 1, 2, 3, 4, 5, 6, and I have some data which needs to be written, right? So what I'm doing here is I am having this in data A present in node 1 and replicated to node 2 and node 3. B is present in node 2 replicated to 3 and 4 and so on. I have like replication factor say equal to 3, and I'm maintaining 3 different copies of the same data on different machines altogether. This is actually something that happens on a data center without V nodes or virtual nodes, right? Physical nodes are present and the data is scattered like this. When I have my data center with the virtual nodes available, right, in that particular case, what will happen is a particular machine, for example, this A thing which was there, which was the node 1, right, is responsible for this data A, F, and E, right? Apart from that, a particular node will be responsible for smaller numerous fragments, right? Now this machine A, or node 1 actually, is not a single machine which is responsible for a single range of data, right? Rather, it is now divided into smaller fragments, smaller partitions. We are terming it as V nodes, which actually can represent various smaller ranges to have the data, right? So this range thing we will discuss about, right, and we'll come back to this slide a bit later on, right? Should be a bit down the order there, but we'll take care of that part. We'll come to this slide later on, that how the consistent hashing helps me there, right? Talking about hashing first, and we'll be coming to that particular slide later on, right? We have those hash methods which are there. We have you know say this MD5 hashing, we have the C3 hashing, we have SHA hashing, different types of hashing which is available. So what we do in that particular case, right, uh, we pick up any particular value, we apply the algorithm on that particular value, and we come up with the hash value of that particular column, right? So what is this, by the way, right? When we say that the data is supposed to be distributed across nodes in a particular Cassandra cluster, right? So this hashing helps us to actually distribute the data across cluster. How? Right? This partitioning thing is actually based on the partitioning key, right? We will learn about this partitioning key when we are gonna discuss about our data modeling session. To have an analogy to understand that part, right? I'll say this thing, right? I am working on an RDBMS, right? I have like n number of records present. All right. These records now belong to a table, and this table has a primary key. I'll have a primary key column which is there, and when I'm actually gonna create an index on top of it, I'll create it on base of the primary key, right? This range to this range, and this range to this range, and so on, right? That is the basic intent of using an index, because it's make my lookup faster, dividing the data into logical partitions kind of thing, if I say that, right? So hashing is a similar thing. What I do, I have a partitioning key column in my table in Cassandra, right? And my table takes up that data, right? Calculate the hash value for that data, right? And then every node, taking the example of this virtual node 1, or sorry, not virtual node 1, physical node 1 is responsible for a particular range, right? And it will distribute the data into that particular node, right? So take example of this particular table. I have this table with 4 columns: name, age, gender, and car that they are owner. The name of this guy is Pankaj, his age is 31, the gender is male, and he's having this car BMW, and so on. I have like 3 separate records with some names and some ages, and then this gender, and then the cars which are there, right? The thing here is, I'm taking this name call as a partitioning key. Might not be the best possible thing, but just for this example, right? I'm taking this name thing as the partitioning key, right? So what it does, Cassandra will calculate the hash value for each partition. So Pankaj will come up to something like this, Priyanka will come up to something like this, Ankit will come up to something like this, and this last name Ashish will come up to something like this, right? This is the example of my data center. I have, like, say for example, I have 4 nodes: A, B, C, and D. Whenever we create a cluster with different nodes, or a data center with different nodes, every node is responsible for a particular range of hash values. You can see that here, right? From certain value to certain value for node A means that whenever I'm gonna have a record, the hash value of whose partition key is gonna be in this range. Node A is going to take care of that particular record. Similarly, a particular range for node B, a particular range for node C, and a particular range for node D, right? Just taking an example, I have written some random values here for the hash thing, right? This hash value, for example, say Pankaj belongs to machine A. The write request will go to machine A. The machine A will commit the data plus will replicate it somewhere else. Similarly, say in order, Priyanka, Ankit, and Ashish, they belong to machine B, C, and D. Why they belong to machine B, C, and D? Say the hash value which is calculated for the partitioning column actually belongs to this particular range. That's how the data is gonna distribute it, right? And every next time I'm gonna have Priyanka again, I'm gonna have same partitioning or same hash value for this partitioning key. It'll again belong to this particular range, right? So that is something which happens there, right? This is not a V node thing, but this is a physical node thing which is there, right? In this particular case, right, in this physical node thing, a particular node is responsible for a particular range, right? But when I talk about this V node thing, a machine is divided into smaller logical partitions called V nodes, and every partition is responsible for a smaller fragment of ranges. Say this in this example, this machine A says divided into, say, 256 default number of partitions. This range will be divided into smaller fragments, right? This range will be divided into even smaller fragments, and so on, right? And hence gonna help me distribute the data like this, right? Why, for example, just taking this thing, in this example I can see node 1 is having A, F, and E, right? So ideally, when I'm gonna have data in node 1 with the V nodes, I should have A, F and E in the data in this particular thing. But I do not have A, F and E, rather I do not have F at all. I have A, E and certain other data as well in this node 1. The reason is, when this physical partition is going to be divided into logical partitions called V nodes, the ranges are not going to be contagious, right? They are just going to be like, I'll rather say this word, random, not contagious, non-contagious. If I say that, not random, non-contagious. How it will help? It will help me in distributing the data even more evenly, right? Data from a particular range is present in this particular partition, data from this particular range is present in this particular partition, and this way, if I have the requirement, or you can say that the scan operation for a particular type of data, not the same node is going to take the burden for all those requests, because that actual range, if I say this minus 9 2 and certain up till certain thing 2 minus 4 6 up to certain particular value for this physical node A is now divided into smaller fragments which may be scattered across any of the nodes. Whenever, say, I have the read request, major read request from this particular range, it's not only node A which is going to actually cater the request. B, C, D can take care of my load distribution for the query from this particular range, because they also have a fragment of this particular range assigned to them. That is the benefit of a V node, a better distribution, a better load balancing. All right. And of course, a better distribution of data makes sense for a better load distribution, so that whenever I have a read request, right, it can be taken care by not only one machine but by multiple other machines. So as we have discussed, in this previous example, that for this particular table, Pankaj, Priyanka, Ankit, Ashish, and a certain age, gender, and car is present for these particular records, right? As assuming that name is the partition key that I have, right? And when writing the data, Cassandra will be calculating the hash value for the partitioning key, right? And accordingly will distribute across the cluster, across the nodes in the cluster. The thing here is, when I'm gonna store this data, Cassandra is actually going to replicate the data across certain other nodes as well. The reason, simple, making it fail safe. So if one of the node is down having the data, I can have the request from the other nodes having the replication. How many replicas I need to take? That is called replication factor, right? How the replicas are going to be placed is called replication strategy, right? Right? Two types of replication strategies I have, right? First is the simple strategy, right? And second one is the network topology strategy, right? A simple strategy with like this brief bullet for this is used only for a single data center. The network topology strategy, on the other hand, is recommended where I have multiple data centers, right? This DC thing, as I have discussed earlier, stands for this data center. Is recommended for a cluster having multiple data centers spanned across multiple geographical locations, or the same location, doesn't matter, but different data centers, right? Simple strategy for a single data center solution. Network topology strategy recommended for, of course, multiple DC clusters. Discussing this thing in detail, right? Simple strategy is used only for a single data center. What it does, it places the first replica or the actual data on the node determined by the partitioner, right? How? Going back a couple of slides, partition key give birth to some hash values based on the value which is there for this particular column, and based on that I will, partition the data across the cluster depending upon what particular range is served by what particular node, right? So the first replica will be placed on the particular node which is going to be determined by my partitioner logic, right? The additional replicas, and we have discussed about this part, the additional replicas will be placed on the next node clockwise. without considering the actual topology. Jumping back a couple of slides here, say Pankaj is gonna written the record or the data for this partitioning key Pankaj is gonna be written onto this machine A or node A, say that, right? According to the simple replication strategy, right, this data for Pankaj will be replicated to machine B and machine C. So this is the clockwise thing which is there, right? This is the simple replication strategy. Just create the replicas onto the subsequent clockwise nodes that I have, right? Without considering anything about the topology, how many racks, how many data centers, I don't care, right? Simply place the replicas to the next nodes available clockwise, right? If the replication factor is 2, the replication will happen only to the machine B because one copy is here in A, the second copy is supposed to be here at B. The replication factor is 3. I need to have the data at 3 different locations. The actual node A and the next clockwise B, E and C, right? And so on, alright? The second one is like a bit more complicated one, and that is called network topology strategy. It is of course used for data centers for cluster which are spanning across multiple data centers, right? This strategy actually specifies that how many replicas I want in each data center, right? Each data center. Taking this example, I have a data center, right, of 4 nodes each, and both the data centers have A, B, C, and D present in both the data centers, 4 machines each. The data will be written to A in this particular data center. The same data will be written to the second machine on the second data center, and the replication will happen across the different machines which are there, right? This strategy of course specify how many replicas I want in each data center, right? The thing is, the same simple strategy will be followed, right? That placing the replicas on the next 2 nodes, but that will happen on both the data centers or whatever the number of data centers I have in that particular cluster. Okay, so same simple strategy spanned across multiple data centers. That is called network topology strategy. So we have discussed about replication strategy, we have discussed about gossips, we have discussed about snitches, right? All these things, and we have discussed about the V node things as well, right? So all these terms actually are gonna help us in actually determining the different operations of reads and writes, right? Okay. So if you remember from the previous session, right, you you might have this slide pictured in front of you where I said that a particular read and write operation in RDBMS was taking something like 300 milliseconds. However, in Cassandra, it was taking just like 15 milliseconds. That's like humongous reduction, 300 milliseconds compared to 15 milliseconds. I guess that is like 20 times less. How does that happen actually? Why Cassandra is so stupid fast, right? What makes it so stupid fast, right? We need to take a look into the right mechanism that happens at the back end, right? What I will do is I'll take up these terms that we have discussed in the previous session, right? And we will discuss about those things there, right? So now we know that whenever we have a write request, we are going to have a record, we are going to have a partitioning. Based on that, I will partition the data across the nodes in my cluster. That's a write request. Now what happens? In the previous slide, I saw that I have 4 nodes present in this cluster, node A, B, C, D. So how does this node looks like? There are these components. You remember something we discussed about this mem table thing, right? That is an in-memory data structure. So you can say it RAM. We discussed about SS table. We call them, you know, uh, uh, I'll say that disk files which are there, right? So whenever we have a write operation, what happens is, and you can see this dotted line, right? And the upper section is the memory part, the lower section is the disk part. So I have a commit log, I have a mem table, and I have a SS table. The commit log and the SS table, they lives on the disk. The mem table, it lives in the memory. So whenever I have a write request, I have a log entry into my commit log. That is a write ahead log, right? You might have heard this term, write ahead log. Whatever write happens here is a sequential write. Take this in mind. So that's not like a random IO, which is going to take a lot of time. That's a sequential write. I need not to move my head here and there and waste my seek time, right? There'll be a sequential write which is going to happen in the commit log. Post that, the data will be written to the mem table. Now, because this is RAM or the primary memory, the writing in mem table will be goddamn faster as compared to writing it into the disk. That is the end of the write operation for me. Had that been in an RDBMS and I had this write operation insert into TBL1 values, Pankaj, age is 31, the gender is M and the car is BMW, that actual write would have been committed onto the disk. Writing to the disk takes time, gotcha, 300 milliseconds, right? In this particular case, the data is gonna be written to the commit log and to the mem table, right? That is it. Not committed to the disk at all, right? That makes the write blazing fast, right? But the thing is, this is primary memory and this is volatile. So when this data is committed to the disk, if you see this, I have this small dots representing an operation called flush. This mem table will have certain size. Say this mem table has a size of, let's say, 100 gigs, if I say that. 100 GB of RAM available. The 80% of this mem table is equal to 80 GB. Whenever the mem table will be 80% full, whatever data is inside this mem table will be committed, or you can say that flushed to the disk, creating a file on disk which is called SS table. And for whatever data is stored onto the disk, I have a lightweight index stored as well, just to identify that in this particular range, token range, or the range of partitioning key values where my data is, as other indexes work, right? So that is something that which will happen only once when my mem table is 80% full, right? Or whatever value has been configured by my admin, right? Or that can be a manual flush that I am doing there, right? So this is something which will happen only once. I will not hit my disk every now and then to get my data. That makes the write blazing fast, right? So what happens? So for example, I have this insert request. Okay, when this is 80% full, the data is written to this SS table. What if I have an update request, right? Or what if I have a delete request, right? Do I, in order to update, do I need to go to those SS tables which are created on disk? If that is the case, there will be a disk IO and it's going to make my operation slow. The answer is no, right? The request will still be persisted only to the commit log, a sequential write which is goddamn fast, right? And then will be placed into the mem table. When the mem table is full, it will be flushed again to the disk, creating another file called SS table. Now, and I'll have two files which is like SS table 1 and SS table 2. But the thing is, if that is an insert operation or an overwrite operation, I may have the data present in SS table 1 and SS table 2. The data in SS table 1, because it was written earlier, is the older data or the stale data, and the one which is written to SS table 2 is the fresh, updated data. Whenever a flush happens, there is an operation triggered which is called a compaction, right? What it does, it picks up those SS files, merge them together based on the partition keys which are there, look up them, club them together, it what it does, it overrides the existing older data with the fresher, newer information, right? And create a new SS file in the end, right? Having all the updated data, right? That is how my update request is going to take care of. And what if I'm going to have a delete request, right? How will I represent that in memory, right? In the mem table. Do I need to do a disk IO in this particular case, a delete request? The answer is no. Because whenever I'm going to do a delete request, I'm going to mention that I'm going to delete this particular record, which is having this name as this Pankaj, right? And this Name column is the partitioning column, so I'll again calculate the hash, and in the mem table, this in memory store, that particular operation will be marked with a special flag. We call it as tombstone. During the merging, for example, say that hash value for Pankaj is existing in SS table 1, and in SS table 2, for the hash value of Pankaj, I have this tombstone present. So this newer timestamp or the newer data has a tombstone associated to that. So the older data for Pankaj will no longer be written to the consolidated SS table, created at the end of the day, and hence you can say that deleted from my desk itself. Okay. Here's the thing again. So if I say that I have some data, 80 GB data in my mem table, I'm going to flush it. Say for the first time, I do not have any SS table in my desk. It's going to occupy 80 GB of space. All right. And then I have, say, 80 GB of mem table again full, ready to be flushed, with 40 GB of deletions and 40 GB of new insertions. Okay. So from the existing 80 GB of data, I need to delete 40 GB of data, leaving it to 40 GB. But this new flush will also add 40 GB of new data, which is going to make it 80 GB again, right? But the thing is, when the flush will happen, my disk space occupancy will be 80 GB for the first SS table and 80 GB for the second SS table. Post that, a compaction will happen, right? If you can see this in this particular diagram, I have my disk space filled with like multiple SS files, right? When compaction happens, the SS files are merged together, making the way for a newer SS table or SS file, right? And the older one is deleted, right? And when the flush will happen, I will have the total disk space occupancy as 80 GB for the first SS file and 80 GB for second, making it 160, right? Now, and when the compaction will happen, the 40 GB will be deleted from existing 80 GB, 40 GB of newer data addition will be made, making another SS table which will be equivalent to 80 GB. So my disk space will fluctuate like up down up down up down, and that's very normal. So while doing disk space calculation in Cassandra, I need to take care of these things as well. If I need to store 1 terabyte of data, I cannot simply have 1 terabyte of disk space. First of all, I need to actually replicate it, say 3 times. So what I need to do, I need to have 3 terabyte of space, right? Now all the space cannot be used to store my SS table. I need some space for my indexes as well. Say 10%. Just taking an example, rough calculation. That makes my 3 terabyte equivalent to 2.7 terabyte. So I need to have something like say 3.5 terabyte actually to store 3 terabytes of data. But the thing is, then I need to take care of the compaction part as well, right? So in order to store 1 terabyte of data replicated thrice, I at least need something like a 7 terabyte of storage space, majority of which will be free after compaction. But in order to make the compaction happen, I do need extra disk space available, right? I hope you are there with me on that particular point. Okay, so that was regarding the write that are happening here, right? Now let's have a look into something what we call it as the replication. We discussed about the replication factor. We discussed about the replication strategies as well. So how it is going to happen, by the way, right? So here's the thing. Here's this example, right? So the replication factor is 3 here, right? In this particular case, for example, say the client is writing the data into my data center 1, right? And I have 2 data centers in my cluster. So if you remember from the previous slide, I'll be using network topology in this particular case, right? Simple replication, not network topology, I'm so sorry about that. Not simple replication strategy, but network replication strategy I need to use in this particular case. So the data will be written to one of the node in the first data center and will be replicated to 2 different data nodes, making the replication equivalent to 3, right? Now, in the wide area network, I need to replicate this data to the data center 2 as well. The request will be sent across to another data center, may be received by any particular node, right? And this particular node, because with the gossiping, it knows that I have this data, it belongs to this particular partition range, right, or token range, which nodes are taking care of that thing. So it will make the write happen for those three machines there, keeping the replication factor of 3 here in data center 1 and replication factor of 3 here in data center 2. Here I'm not actually, created this diagram with something like that ring topology, making sure that, okay, it write it clockwise, but actually it happens in this particular way. All right. Okay. Data is written. Great. Right. But that's not the only thing that I'm supposed to do. Once done, of course, I need to do something like check that or perform any operation on my data. Do a read on top of it, right? So reads are actually, they're similar to my write request as it happened in Cassandra. They also happen with something called a partition key. All right. So whenever a partition key as is required to read the data, I will send a read request. Select star from my table where name equal to Pankaj or Priyanka or Ankit or Ashish or whatever XYZ. Right, this is the partitioning column that I have. We'll discuss about that thing in our modeling session in detail, right? So how the read request happen? Whatever read request comes, first of all, it go through a Bloom filter. I hope you have heard about this Bloom filter, an algorithm just to identify that my data exists or not on this particular machine, right? So it gives that yes or a no. That actually saves all these things, all these operations of looking into this partitioning key thing, looking into the partitioning index, identifying the data where it is stored, and then returning. If it is a yes, and again there is this dotted line identifying the separation between the memory and the disk. If the Bloom filter says yes, right, I'm gonna have my data in the in partitioning key, right. This is a cache which is there. For example, if I have just uh, uh, issued a read operation for this partitioning value which is equal to Pankaj, right, the partitioning key information will be stored there in the memory in the cache, right, for the recently, right, we call it as most frequently used MFU, right. So the most recently MRU, most recently used data, that will be there in the partition key column. We'll look up into the partition key cache if it is present there, right. We'll have the lookup into the partitioning summary where the data is present, and we'll have a look into the partitioning index, which will actually send us there onto the SS table where the data is stored, and we'll have look up into the data and return it back, right. So if the data is there in the partitioning key cache, means it is the most recently used data. This data is something which was just actually requested a couple of minutes back, right. What I can do is I can directly jump to this compression offset part, right, getting the exact location of where the data is stored on my SS table, and then return the resulting set. Okay, but the thing is that might not be the case, right? If that is not the case, and my data is not something which was like most recently requested or most recently used, and is not in the cache, because of course cache is something like a limited commodity and is gonna have just the just the recent data requests there, right? If it is not there in the partition key cache, I will look into the partition summary, right? Partition summary will hold all the information regarding that which particular data is present in which particular SS file. Post that, I will have a partition index, right, having the exact locations to look for which particular SS table to get my data. And then this compression offset, because SS tables are something which are you can say that compressed files, I'll have the exact location as the index work, will actually look up for that data and will then return the result set from there. Okay. So this partitioning key cache, we call those tables that like in memory, right? So what happens with in memory thing, the recently requested result sets, the partitioning information or the metadata information, or you can simply call it as the indexing information, is stored in memory for faster lookups, right? Making our operation even faster. All right. Taking this example, right, when a read request for a particular row is arrived, right? First of all, I'm going to have multiple SS tables, and all those SS tables, for example, agar, if I have this from this partitioning index, I came to know that this particular key is present in more than one SS table. What I need to do is I need to have the information from both the SS tables. Plus, I also need to have the information from the mem table as well, right? And I need to look that what is the most recent one. Okay, the most recent request with the latest timestamp is supposed to be something which is the updated data, right? That is something which will be returned back to the client, right? So the client requested a read request. The request will hit the SS tables, right, and then the mem table, of course. The most recent one, right, will be produced, right, and will be returned back, right? So the first preference is always given to the mem table. If I can find anything inside the mem table, means yes, okay. So this is, of course, what is in the mem table is something like which is unflushed, right? It is the latest one. So the read request is you know catered from there, taken care from there. If it is not there, right, I take it from the SS tables, whatever is with the latest timestamp, right, merged together here. The one with the latest timestamp is kept and is returned to the client. All right, let's go ahead and have a look into this particular diagram again. So a particular client is writing the data, and some other client at the same time is issuing a read request. Might be the case that the data has been committed to this machine, which is 10.0.0.1, right, and has not been committed to 10.0.0.2 and 10.0.0.3, has not been replicated yet, right? Now when the read request will come, any of this particular machine may actually cater that request, and if the request is catered by a machine which actually is not having the updated data, might result in some consistency issues, right? We'll have a look into the consistency levels that we have for the writes and the reads, right? And we'll see that what all options we have here, right? And how do they actually impact my reads and writes. All right. So here's the thing. For write consistency level, the first thing is this level is called all. Okay. Whenever a client requests to write the data, and the replication factor is 3, means 3 nodes are responsible to take care of this particular record. Whenever I mention consistency level of all, it means that the write must be written to the commit log and the mem table, right, on all replica nodes in the cluster for that partition. That all the 3 nodes should actually have that data, and the confirmation to the client is provided only when the data is written to all the 3 nodes which are supposed to take care of the replica, right? The benefit of that, it provides the highest degree of consistency. All right, say for this example, the replication is supposed to happen clockwise. The third machine is down, right? And I say that a write will be committed only when the data is written to all the 3 machines. Using all will actually give me the best consistency, but at the same time the lowest availability, because I cannot cater the downtime for a single machine, right? If one machine is down which is supposed to have the replication factor, my write will not be committed, right? The second thing, or the second level that I have, is called a quorum, right? In simple word, we call a quorum as a majority. So if the replication factor is 3, the quorum will be equal to n minus or 1 divided by 2, whatever like that, right? So for a replication factor of 3, the quorum will be of 2 nodes, right? A write must be committed to the, of course, the commit log, yes, right? Of each node which is going to hold the replica will have this commit log and the mem table thing, right? So this write must happen to the commit log and the mem table of at least the quorum, or you can say that if the replication factor of 3, at least 2 machines should have this data written, right? And the confirmation message will be there, sent back. It provides a very good consistency, if I say that, not the best of it, but it can actually also add this kind of another vertical to my availability. Or you can say that uh, if one of the node is down and the data is committed to two of the nodes which are available, I can still say that my write has committed. This is like a trade-off. I might be trading it off on the consistency level a bit, but I'm actually gaining on the front of my availability level. The third consistency level while writing the data is any. That for example, three nodes are supposed to have the replica for this particular data, this particular range, right? If I mention the consistency level to be any, and we'll see that how do we mention these consistency level during our data modeling session, or when we are going to work hands-on with the SQL part, right? When I say any, it means that whatever the replication factor I have, if the data is written to at least one of the node, right, my write should be considered as committed. This actually guarantees the highest availability, because whatever, even if one node is available, I can write the data there, right? You know, very fast write operation which is there. But on the other hand, actually I'm trading off with the consistency. The other two machines might be down, or might take some other, might take some time to replicate the data, right? And might not be in sync, right? That means I will have the fastest of the writes in consistency level of any, but lowest of consistency. Apart from that, we have the consistency levels which are called local quorum, right? And this 1, 2, 3. We will discuss about that 1, 2, 3. Actually, this 1, 2, 3 is like three consistency level used, right? A local quorum is actually is which is, you can say that, something similar to a quorum, right? In quorum, we said that a replication factor of at least the majority, 51% of the replication factor. For 3 it is 2, right? Should be actually satisfied. Local quorum is something which is used in multiple data center clusters. So if I go back a couple of slides back, if I see this, I have data center 1, data center 2, 3 nodes from each data center are responsible to have the copy, right? A local quorum states that if I have the write happened to, at least two of the machines in one of the data center, I should make it as a write commit. All right. Okay. Now this consistency level of 1, 2, and 3, right? A write must be committed to the commit log and the mem table uh, on a quorum of replica of nodes, right? So that is something like 1, 2, and 3, right? 1 means that write must be written to the commit log and mem table of at least one replica. So in case of 1, 2, and 3, a consistency level of 1 means hard code ones, not any, right? 1 means data must be written to the commit log and mem table of at least one node. Okay. In case of 2, it should be written to at least 2 nodes. In case of 3, it should be written to at least 3 nodes. Got that point there? All right. Okay. Similarly, right, I have the consistency levels for reads, right? And they are, you can say that, pretty much similar to my writes, right? But I need to see that how actually they happen, right? So I have a consistency level of all, right? In this case, the data will be returned to the client if every replica has responded. The read operation will fail if any of the replica does not respond. The benefit of all as a consistency level while reading the data. It is the highest consistency possible that you can actually access. Why? Might be one of the three replicas has the most updated data. And when you are using all, of course, the data will be merged from all the three requests and one with the latest timestamp will be sent back. So if I am using all, I'll be getting the highest degree of consistency available, but at the same time, lowest degree of availability. All right. Then I have like each quorum or local quorum. They are very much similar to each other, right? Uh, Returns the record once a quorum of replicas in each data center of the cluster have responded. I have the replication factor of 3. So the 51% or higher, you can say that the quorum majority is something like 2 nodes out of 3. When 2 nodes out of these 3, any 2 have responded the data, I can actually cater that read request. Okay. quorum, right, is very much similar to your each quorum or the local quorum thing, right? Returns the record when the quorum of replicas have responded from any data center, right? Each quorum and quorum, they differs in a way. Each quorum says that I should have the response from a quorum of or majority of the nodes from each data center. Local says that to whatever data center this request goes to, two nodes from that data center should respond. Quorum means that from any of the data center I should have a quorum of node responding to my request. If that is happening, 2 out of 3 nodes are responding to my query, I will actually return the result to the client. Alright. If only one of them is responding, the read request will fail. Right. Similarly, I have 1, 2 and 3. They are of course very much similar to the 1, 2, 3 that we have discussed earlier in our write consistency level. So 1 states that if one of the node is responding, right, in that particular case, uh, even I don't care that the rest of the nodes are responding or not responding or whatever it is, right? If one of the node is responding to my request, right, I can simply cater that request, return it back. All right, 2 or 3, they are very much similar to 1. So if I have the request from at least 2 or at least 3, right, I can send the data back to the client, or the read request is catered for the client. Local one, very much similar, right? So there are multiple data centers if I say, right, and if I'm sending the read request, if from the local data center any of the node is responding to my request, the read request is catered. I need not to take care of anything else, right? So this is a document which is here, right, and this talks about the example of the consistency levels, right? So let's have a look into this. So I've created this Word document, right? All right, so this is the Word document which talks about the consistency levels, right? So here is the thing, talking with examples, right? So it talk about a single data center with the consistency level of quorum, right? We understand that quorum is the majority, right? For example, the replication factor is 3, right? So 2 out of 3 replicas must respond. In that case, if you see, this is the client, right? This is the coordinator node, right, which is going to take care of that. 1, 3 and 6 have the replicas available for my data, right? In quorum, right, what will happen is I will actually read the data from 1 and 6, or you can say that any of the two nodes, if any of the two nodes are responding, I can return the request back, right? Read response. The third machine, right, the third replica will be actually contacted in the back end, right? And what will happen in that case is we will see that which of the 3 nodes have the most recent data that will be identified by the timestamp, right? And what will happen in that particular case, whatever machine has the most updated data, right, it will replicate the data to the other machines, which is called as a read repair. All right, that might or might not happen. That will happen only in the case where the data is out of sync, but in majority of the cases it will not be the case, because whenever the write request is there, the data is supposed to be replicated to these machines, right? So that's not the issue there. But in case if this is out of sync, right, I have written the write operation with the consistency level of any, right, and it has not been replicated in time, or due to any other reason the machines were down and they have like out of sync data, this read repair thing will actually you can say that update the data on all the nodes. A single data center with the consistency level of 1, right? In this case, any of the machine which is going to respond to my data, right, I am going to take care of that, right? And whenever it is responding, for example 1, 3 or 6, whosoever responds the first, whosoever responds first, right, the fastest, the request from that particular node will be sent back to the client. A 2 data center cluster with the consistency level of quorum. In this particular case, if you see this, right, so the client has requested for the data from this node 10. So or we can say that the read request is taken care by this is the data center alpha and this is data center beta, right? In data center alpha, machine 1, 3 and 6 have the replications. In data center beta, my machines 4, 8 and 11 have the replications available, right? So in this particular case, the consistency level is quorum, right? So in that case, I need to have the response from two nodes from each data center in order to send the request. All right. So it will take care of the data, right? And once the quorum of the nodes are responding from the data centers, it will send it back. And of course, this read repair will be taken care at the back end, merging the data from all the nodes parallelly, right? A two data center cluster with the consistency level of local quorum, right? In the local quorum case, right, this client is requesting for read request from data center alpha. What it will see, that if any of the two nodes or majority of the nodes from this same data center are responding, I will send back the data. I am not going to look for the data in the remote data center, right? But of course, the read repair thing will be in place as it is there with the quorum level, right? A two data center cluster with a consistency level of 1, right? Here is the thing: data center alpha, data center beta. The client request for the data, it will look for one of the replica for the data present and will respond it back to the client, right? The rest is the read repair thing, which will actually take care of the data according to the data which is present, which is received from the different nodes, right? After actually catering the read request, the client is not made to wait for the read repair thing to happen. That actually happens at the back end, right? So the response time is not hampered with this read repair thing, right? So this is a two data node cluster with the consistency level of local 1, right? In this particular case, I'll look for just the local replica, will return the thing, and I'll keep on doing the read repair, of course, in the backend without halting my say that read operation, without actually hampering it, without actually doing anything on top of it, right? Without making it wait. So quorum level that we have discussed, this is like a simple formula which is there, right? The quorum level writes to the number of nodes that make up a quorum. A quorum is calculated and then rounded it down to a whole number. For example, sum of replication factors divide by 2. Okay. So for example, if I have like uh, uh, replication factor is equal to 3, right? And replication factor is equal to 3, and this will be divided by 2. 3 divided by 2 is equal to 1.5. A 1 will be added, that makes it 2.5. Round down, it will make it 2, right? What is meant by this sum of replication factors, right? Let's get back to my document once again to understand that part. Which example should I take? There we go. Two data center cluster with the consistency level of quorum, right? So for example here, this is a two data center cluster, right? And the replication factor for each data center is 3, right? Two data centers, 3 for each data center, the replication factor, and the sum of replication factor will be equal to 3 plus 3 equal to 6, right? This 6 will be divided by 2, which will give me 3. A 1 will be added, 4, right? So what is the quorum for a replication factor of 3 for two data centers? That is equal to 4, right? So you get the quorum part. If it is good, I will discuss about the read repair thing. All right, so let's go ahead, right? I can take up any example in this particular case, right? So take an example of this thing, right? So the client has requested for the data from this particular node, right? Or you can say that this particular node has taken up the request. Because of the gossip, this node knows that this particular partition range is taken care by which particular node, right? So it will redirect to that node to get its data, okay? So say this example that in this particular case, my consistency level is quorum. So as soon as I have the request from 4 nodes, right, across the data centers, right, which is equal to the quorum, I will return to the client with the data it has requested for. From these 4 nodes, there are two options. Either the data is in sync or the data is out of sync, right? If the data is in sync, right, what will happen in that case, it will be merged together, right? In that case, because the data is in sync, every node has the same instance of the data available, and the data is returned back to the client. take this example. The data is not in sync. One of the node has like the updated data available to it, right? When the coordinator node will have the response from all these four nodes, the data will merge together and the most updated data or the data with the highest timestamp will be returned to the client because this is the fresh most data from whatever nodes have responded back. But here is the thing, buddy. When I said that a consistency level of all is something which guarantees the highest level of consistency. Why? In this case, I am satisfying my quorum from node 1, 3, and 6 and 11. 4 out of 6. And I'm sending my return results back to the client. Thing is, might be this 4 and 8 or any one of them has more fresh data as compared to these nodes. What this coordinator node do, right? It actually, at the back end reads the data from this 4 and 8. But the thing is, it do not wait for these 4 and 8 machines to return the result back to the client, so that client do not waste its time there. But it does read the data from here, right? Now, when I have the data from all the 6 nodes, right, I will have the every possible value from whatever nodes that are holding this data, right? When I merge this data, I will have the most updated data according to the most recent timestamp, right? And what will happen in that case, that data will be propagated to every node, to 1, to 3, to 6, to 4 and 8 and to 11, so that every node now has the most updated data and they are in sync. That is called a read repair. That whenever a read request is sent, right? Okay, the read request has been satisfied according to the consistency level mentioned, but the thing is, the Cassandra cluster at the backend will make sure that all the copies are in sync, so that the next time there is a read request and any of the machine is satisfying the consistency level, the client do not get the stale data, right? In this particular case, there is a possibility, slight possibility of sending the stale data to the client, right? In order to trade off for the high availability and faster read times, I am actually, you can say that, compromising a bit with my consistency, right? So we have discussed about the components, the replication strategies, the V nodes and other things, right? And we have discussed about the read and write and the consistency level in detail.